Hey, welcome to our second video lecture in my digital audio signal processing course. And just like the first one, this has a 0 number. So this is really not part of the course. This is just a courtesy review. And this first unit is all on DSP stuff. So in the next video, we'll get into coverage of, and the rest of the unit, we'll get into some coverage of various things that are more just general DSP things that will be useful to us and not specific audio things. All the other units are much more audio specific things. So in this one, we're going to review some of the basic ideas in MATLAB for DSP. I'm not going to cover them all, but I'll cover the main ones. And we already did see a few back in -0A. We saw freq Z and we saw Z plane. I think those were the main ones that we saw. So I'll allude to each of those here again. So MATLAB, right in its name, it's telling you matrix laboratory. So it was originally developed for doing matrix computations, and then somewhere along the way quickly became kind of the go-to tool for doing DSP computations. So it's got lots and lots of commands that are focused on DSP, especially if you have the signal processing toolbox. So much, if not all, of what we're going to talk about here will require you to have the signal processing toolbox. There's a version of MATLAB called Octave. It's not really a version of it, it's kind of a knockoff of it. So most of what I talk about here would be available in Octave as well, if you want to try that out. That's freely available, but requires a little bit more independence in installing it and using it than MATLAB might. So here's the thing, there's tons and tons of commands for DSP, and each one of those commands has many ways to call it, depending on what parameters you have to put into it, what form they're in, what units they're in, and what it is that you want out of it. So it can be very complicated. And here's the thing, if you're not careful, you can call most of these functions in some way that isn't what you think it is. And so you can get into trouble pretty quickly. And trust me, I've discovered that on my own many times. I've called it one way thinking this is how it's going to work, and then it does something entirely different, but I might not know that. So long ago, I decided that I was just going to find pretty much one way to call every one of the commands that I use all the time. And so for each one of those common commands that I use, I will nail down one way that I will call it, and I'll know how to do that one. And then I'll always try to do it that way. That just helps me. And I would encourage you to do the same way. If you want to know the other ways to call them, you can always go to MATLAB's help, type help, and then the command name on the command line, and it will show you all those ways, all those alternate ways to do it. But you have to kind of be clever and knowledgeable to know what it is that it's telling you. The MATLAB help leaves a little bit to be desired. So I'm just going to share with you in this note set my preferred ways to call the most common commands for DSP. So one thing we often want to do is compute a signal at a bunch of different time points. So in the previous note set, we focused on DSP concepts, and we talked about sampling, and we said that we need our signals sampled at a specific rate or at a specific interval, and that interval is 1/fs. So here's two ways that I commonly compute a time vector properly spaced for a given sampling rate. There are other ways to do it. I would caution you to be careful with lin space. It can be used, but it's a little tricky sometimes. So I try to avoid using linspace. I just do it like I would normally think about it. I want things spaced every 1 over fs. So in this form, I create a sequence of integers from 0 to n minus 1, and then I divide those by fs. So I have a bunch. So each element in that result is an integer divided by fs. So that's going to give me things spaced by fs. That form is handy when I say, oh, I need a time vector with this many samples. That would be the capital N here, which I don't show defining it up above, but you would have to define that previously. There are other times when I want to create a time vector that goes from 0 to some particular end time, capital T. So again, I would have had to have defined the variable capital T somewhere prior. And so a form that I like for that is to go 0 to T with a spacing of 1 over fs. So that's just the double colon format for MATLAB. The thing in between the two colons tells MATLAB the spacing that you want, and you have a starting point and an ending point. So that's very nice. Keep in mind that if capital T is not an integer multiple of 1 over s, the last point will not be equal to capital T. I believe it stops just short of that. So keep that in mind, but that's a nice way. Okay, now you've got a time vector, and you might want to use that in some mathematical function to create a signal. And the most common mathematical function to use to create a signal is a sinusoid. And so here I'm just illustrating setting the frequency to 1,000 hertz. And then you don't have to do this, but I just randomly pick a phase. So with the command that I have there, it'll the rand11 will give one number that's randomly selected between 0 and 1 times 2 pi gives you a random phase between 0 and 2 pi. And then I just use the t vector that I created above, one way or the other, and I use the phase and the frequency. So since that's in hertz, right, since this is in hertz, I have to put the 2 pi out in front, because everything in front of a t in a sinusoid has to be in radians per second, so that radians per second times t in seconds gives you radians, and this phi has to be in radians. So yeah, books tend to show the phases in degrees, but when you plug them into the MATLAB and into math functions, they really need to be in radians. And then we can put an amplitude out in front. So I just picked 2. And then I'm saying, hey, use lowercase symbols for time signals. That's what we do in our theory. So if you do that in your code, that helps you, as well as anyone else reading your code, keep track of, oh, it's a lowercase thing, so it's a time signal. Oh, it's an uppercase thing, we'll see on a subsequent slide. Oh, it's an uppercase symbol, so that's probably something that's a Fourier transform or something like that. And then if we want to plot it, the way we've created it here, since x is made from t, x and t will have the same number of elements, so we can plot them. When you do the plot command, the two things that you put in there have to have the same number of elements, and sometimes you run into trouble when one of those is a column and the other is a row vector, so you have to watch that. So if MATLAB starts giving you errors, check sizes and check orientations of the things inside your plot. Notice that it's the horizontal variable first and the vertical variable second. That's just how MATLAB does it. And at this point, since I've talked about row vectors or horizontal vectors and column vectors or vertical vectors, MATLAB's functions tend to work with columns by default. So if it's making something, it tends to make it as a column unless you tell it to do something else. I like to work in rows. So sometimes I get weird things. Like, for example, later we'll talk about windows in FFT processing, and MATLAB's commands that create windows create column vectors. And that runs into some problems with me because I'm creating a row vector here, which then makes that a row vector. And if I then try to apply a column vector window to that X signal, MATLAB will give me an error. So you have to be aware of that. But I like rows because that's kind of what I think about a signal, right? We plot it horizontally on our page when we look at it in conceptually. So that's what I do. You can try something different if you want and stick with all columns. But most of the commands and examples that I'll show you in this course, I'll stick with my preference for columns. Okay, so the FFT command is a huge, powerful tool that we use, and we use it to plot the spectrum of a signal. And when we get into the next set of notes, we'll start looking at the FFT in how to use it in a lot more detail. And then the note set after that, we'll learn what goes into the FFT command, what's the mathematics underneath it. So once we apply the FFT command, we want to plot the spectrum. And so in a signals and systems class, we might insist on showing spectras with double sides, right? Positive frequency side and negative frequency side, just to drive that concept home. So sometimes we do want to show that here, but right after I show you this double-sided one, I'm going to show you the single-sided version. So if you do want to show both positive and negative frequencies, this would be the way to do that. And we say that this is computing and plotting the double-sided spectrum. So I'm going to assume that the vector X already holds the signal samples. And, in this case, I would generally have those in a row vector, although I think this code would work even when X is not in a row vector, but is in a column vector instead. So here's the FFT command right there. And notice that I plug in the time vector. See, lowercase, easy to keep track. I plug in the lowercase time vector for the signal in there. And then in this FFT command, the second argument that I always put in is an integer. Generally, we think of that as a power of 2, although MATLAB is pretty flexible with what you put in there. But for what we're going to do here, it must at least be even. So it might not be a power of 2, but I like to at least keep the NZP to be even, as you'll see as we progress into the single-sided spectrum type of thing. So let me back up here and say, so that's setting the zero padding. And at this point, you should have learned about that. We'll go into a little bit more detail on that in the next set of notes. But zero padding we talked about in the previous video. It allows us to control the grid error. So it gives us FFT points that are more closely spaced throughout the -pi to pi range. So we put it in right in the FFT command. We don't have to physically tack on zeros to our X vector. The FFT command has a feature that does that. But here's the catch. The number that we put in here, I guess I didn't say it here. The number that we put in here, maybe I say it in just a little bit, must be bigger than the number of elements that are in X. Otherwise, it's not going to zero pad. So it zero pads out to the number of that NZP. And I think I'm just saying this first, and then the notes will tell you about the NZP things. So notice that I use lowercase here and uppercase here. That just helps me and you, and it helps you help me keep track of what you're doing in your code. Okay, yeah, so here we go. Here's where I tell you that NZP, in order to actually do zero padding, must be greater than the number of elements in X. So there's a command that you can run to find out how many elements there are in X. And then this is just my general rule of thumb. In order to get the grid error down to a reasonably small amount, my rule of thumb is that I usually put in an NZP value that is something on the order of 4 to 5 times the length. Now, remember, sometimes in non-MATLAB world, our software for FFT may require this to be a power of 2. So you look at 4 times or 5 times, and then you bump it up to the next largest power of 2. But at least in MATLAB, we need that to be even. So take 5 times the length or 4 times the length, and then bump it up to be an even number. That just ensures that you have enough FFT points so that your spacing is fine enough. Usually, sometimes we need to do lots of zero padding to make things work. And I'll comment on some of those cases as we go through. And this is just a comment saying that MATLAB is flexible on this, but other non-MATLAB software may be very demanding that the thing that you put in for the amount of zero padding, as well as if you're not doing zero padding, the length of your signal. I should comment on one thing. If this is not satisfied, then be careful. What this does, this FFT with a number NZP less than the length, is it actually truncates the signal to that smaller number of samples, then takes the FFT. So sometimes that's convenient if that's what you want to do, but generally that's not what we want to do if we're trying to get a nice spectrum. Okay, so here's some commands once I've created this X. Oh, and I should comment on the FFT shift here. The FFT kind of gives you the DFT points in an unusual order. It makes sense when you see the theory of DFTs and the theory of FFTs, but the point is that it puts the positive frequencies first, and then the negative frequencies are at the end of the computed vector, and we don't normally want that. So the FFT shift just flips those around and puts those in the right order, puts the negative frequencies starting first with the most negative location first, and then up through frequency of 0, and then up through the positive frequencies. So the FFT shift command does that for you. And then we just need to create a vector to plot this against. So we need a couple things here. We need to make sure it's the same length as capital X. We need to make sure that it starts at minus pi. So this FFT shift brings the minus pi frequency down. And so the very first element in your result is at a frequency of minus pi radians per sample. Therefore it ends just shy of pi, because remember, minus pi and pi are the same frequency and they don't both show up. So we are interpreting that frequency as minus pi rather than pi. That just comes from how MATLAB does the FFT shift. So I need the right number of elements in W. I need it to start at minus pi, and I need the spacing to be the correct spacing, which in terms of radians per sample, the spacing between DFT points is 2 pi divided by NZP. That's just taking the minus pi to pi range and slicing it up into NZP points. So that's where that comes from. So this structure here just creates a sequence of integers. Here's, you can see why I'm demanding this to be even. So it just starts at a negative integer and goes up to that same positive integer, but actually one less. So that gives us the starting point. And you can see that this 2 and this 2 in principle cancel each other, and the NZP and the NZP cancel each other. So this goes from minus pi up to just shy of plus pi, which is exactly what we want to do. So yes, there are other ways to compute this W vector. I've found that many students stumble upon other ways to do this that are not quite correct. So you'll have slight little errors in your frequencies. And sometimes that's not a big deal if you're just taking a quick look at the spectrum, but sometimes it can be an important error that you need to avoid. So this is how I do it. I do it this way every time, and it always works. So I would encourage you to do that. And now I'm just going to plot both the magnitude and the phase. So remember, this is a Fourier transform, so it's complex valued. So I need to take the absolute value of it. And then we almost always want to plot these things in dB, plot the magnitude in dB. And this is not a ratio of powers, so I do a 20, not a 10. And then this is my little trick. I take the frequency that's in radians per sample, and I divide it by pi when I make the plot. So it's really going to go between -1 and just shy of +1. That's just my little trick. So then I get nice little grid markers at like pi/2, because that's just a half. So MATLAB will give me markers at places like a half and a quarter and 3/4, or maybe 0.2, 0.1, 0.2, 0.3, 0.4. Those are nicely interpreted as 0.1 pi, 0.2 pi, and so on. And this subplot thing just allows me to put two plots on one figure. Okay, so that's nice. And there are other ways to call that, and you can do a help on that to see what that means. So this will give us two plots, one over the other one. And then, so that's plotting the magnitude. I'm going to plot the phase in radians. Sometimes we want to show it in degrees, so you can just do the common conversion that pi radians corresponds to 180 degrees. What's this unwrap command? Well, I should say the angle command here is nice. We're not doing atan or even atan2. There's a nice command called angle that will avoid some of the pitfalls of atan, and is a little easier to use than atan2. So I encourage you to use the angle command there. It'll give you the angle in radians, but that angle will lie between minus pi and plus pi. So if suddenly that phase is at something close to plus pi and it tries to go a little bit further positive, so might try to go to say 1.01 pi, well, the angle command will say, I don't understand 1.01 pi, and it will convert that into its corresponding value that'll be close to negative pi. So it might be negative 0.99 pi. And so you get a jump, and that jump covers a range of 2 pi. So what unwrap does is it just goes through and it looks for those jumps that would occur from the angle command, and then it just adjusts for those. And we'll see some plots as we go through the course where I talk a little bit more about that, especially when we get into talking about linear phase filters in an upcoming video. So that's that. And then I, again, do my little trick with W divided by pi. So that's plotting everything versus discrete time, or at least a normalized discrete time frequency. And so that's just telling you what the unwrap command does. You can read more about that if you want. Lots of times, though, look, we're dealing with audio signals. They have a connection to the physical real world. That connection is through the sampling rate. So we hardly ever want to look at something plotted versus frequency in radians per sample. Maybe every once in a while if we're just working out the details of the design of a filter and want to make sure that the filter design I'm getting matches up to how I specified the parameters in terms of discrete time frequency, I'd want to do that. But most of the time, I just want to look at this corresponding to its equivalent continuous time frequency. So I'm going to need the version of this that is in Hertz. So here's one way to do it. I can compute this first, and then remember that pi maps to Fs/2. So I can take this W vector here, and I can take W and then divide it by pi. and then multiply by fs over 2. So that normalization makes pi become 1 times the fs over 2 makes the pi position become fs over 2. So I could do it that way. I could use this and create W and then convert into F in Hertz, and I do that sometimes. But more often than not, I'm targeting right straight away. I want my continuous time frequency vector. So I just do the same thing, series of integers, just like we said before. And then I divide by NZP. So now this becomes minus a half, and this becomes minus a half minus, or a half minus minus 1 over NZP is the right way to say that. So when I multiply that, the sequence of integers times fs, I get something that will go from minus fs over 2 up to just shy of plus fs over 2. So the same things that correspond to the minus pi and just shy of pi that I had up there. I like that little rhyme. It helps me remember. Minus pi to just shy of pi. And then I do everything else the same, except I don't have to normalize the F down here because I want to see it in actual Hertz. Now, I might normalize it by 1,000 if I want to make my plot in kilohertz, or if I were not in audio, I might want to normalize by a megahertz and plot in megahertz. But in audio, we don't generally need to go that high. But more often than not, I just leave it as F, but sometimes I'll normalize it. And so everything else is the same there as we saw before. So that's all double-sided. So I do the FFT, I do the FFT shift, I create a frequency vector that goes both negative and positive. Through the negatives first, then through the positives. Okay. More often than not in audio, since we know we're dealing with real valued signals, we know that their spectra are going to have symmetries, even symmetry for the magnitudes and odd symmetries for the phases. So we don't really need to worry about looking at those negative frequencies. They just get in the way. And as I'll show, when we want to do a log frequency axis, the negative frequencies really get in the way. They cause a problem. So lots of times we're just interested in looking at single-sided spectra, so just the positive frequency side. So notice that I still do the FFT the same way, but no FFT shift. So now remember, because there's no FFT shift, the first half of this vector is all the positive frequency components. And the second half of that vector, and I'm using half a little loosely here, I'll comment on that just a minute. The second half of the vector is the negative frequencies, which we're throwing away because we only want the positive ones. So I say grab the first half plus 1, right? So that's why I'm going to 1 colon 1 plus NZP over 2. That will actually grab the 1 point that if we did FFT shift becomes minus pi, but now it's just sitting there as if it's at pi radians per sample. So I grab that. You could maybe not grab that, in which case you'd leave off the plus 1 there. Then you'd only go out to just shy of pi. But I tend to grab the pi position. Now I need to modify this. So now I'm going 0 to NZP over 2. So NZP over 2 times 2 pi over NZP takes me out exactly to pi radians per sample, okay? And it will turn out that if you do all this correctly, these two vectors will have the same length, and I can plot them. So now I'm going to plot, and I'm going to do my same little trick with normalizing the omega, and I'm going to plot the magnitude in dB, and we would do a similar plot for the phase. I just didn't show it here. Okay, now in audio work, we almost always want to see things in terms of hertz rather than radians per sample. So here's the same thing. I go 0 to NZP over 2 times Fs over NZP. Or if I want both, I could create this and then divide omega by pi, and multiply that result by fs over 2, and I'd get the same thing. Okay, so there's how we do that. But in audio, since we're generally interested in things that go from really low frequencies, like down around 20 hertz, or maybe even a little bit below that, because that's the lowest frequency that a human can hear, all the way up to 20 kilohertz. So that's a huge range. And if we plotted it on a linear frequency axis, you would not be able to see much of the interesting activity down around 20 and 50 and 100 and 200 hertz. Those are important frequencies for audio analysis. So we want to look at this on a log frequency axis. That's one of the beautiful things about a log axis, is that it allows us to see a broad range of the variable, in this case frequency, on an axis without losing track of what's happening at small values and what's happening at large values. The one downside is that we can't show zero. We can't show f equal to 0 on a log frequency axis. So we just need to plot down far enough that makes sense. So a common error I see is for students to make this plot go down to like 0.1 hertz or something like that. That's, unless you have a real reason to do that, you probably shouldn't go down that far. Even 1 hertz is pretty far down, right? 1 cycle per second. No one can hear that. So 10 hertz is probably a good place to start your logarithmic frequency axis for audio work. So anyway, one way we can do that is we just create the f this way. And then we do a semi-log f, or semi-log x. So that will say take the horizontal axis and make it semi-log. And then we use the 20 log 10 here. Remember, log 10 dB is a logarithmic quantity. So we're really doing log magnitude versus log frequency. It's just that we're seeing the log frequency explicitly, and we're seeing the log magnitude in terms of dB. So, and we could do a similar phase plot, although obviously not in log 10 of the phase. Now, when you run that command, since there's going to be a 0 in this f vector, there will be a little warning. MATLAB will tell you, oh, I can't plot log of 0 on a semi-log axis. And so it will just discard that point, but it'll give you a little warning on the command line. So when you're running commands in a function or in a a script function or a script file, always go look at what's going on back at your command line, because MATLAB will give you warnings that it won't stop your work, but it will give you some warnings, and those warnings might tell you that you're doing something not quite right. But you might see that warning, like in this case, and say, yeah, okay, that's perfectly fine. Now, you also, depending upon the value of NZP that you used here, this will throw away the 0 point on the f-axis, but the first point may be at a frequency that's just too low for you to care about. So you can always adjust that by using MATLAB's axis command. So there is an axis command that will allow you to zoom in to a certain range of x values and a certain range of y values. And there's also xlim and ylim, which will do similar things. So that's what I'm saying here. It can also lead to sparse point spacing at low frequencies. So you might need to bump up 0 padding more than that 4x or 5x that I suggested before. And you then get very dense spacing at high frequencies. So the FFT command is really not well suited to doing this, but we often just do it and live with the results and just 0 pad until we get what we want to see. Okay, so that's finding the spectrum of a signal. If we want to think about how that spectrum gets changed by a filter's frequency response, our first step is to think about the transfer function and use the freq command. So really the freq command is giving you the frequency response. So it's right there in the name, freq, and z is telling you that this is for a continuous time filter. There's a freq-s that I'm not going to talk about here, and that's what we use to get the frequency response from the transfer function coefficients for a continuous time filter. So again, remember, there's many ways to call freq-z. I'm showing you my main go-to way. I almost always do it this way. It's very rare that I do it a different way. And I just know how to always manipulate things to enable me to call it this way. That I can remember. I can never remember. So if I wanted to do this, how do I call it? And I don't want to look things up. So I know this way, and this is what I do. So I've got a transfer function here in Z inverse form. And so I've got a sequence of coefficients in the numerator and denominator. I put those into a vector, making sure that the first ones are whatever are on the z to the 0. So if there isn't a z to the 0 term, I need to put in a 0 in this vector to account for that. And then just all the way out. So these two vectors might be different in length. And if there's any missing powers in the middle, I need to put zeros in for those. Okay, so I've got that. And if this is an FIR filter, then none of this will be here, and more than likely this A0 will be equal to 1. So this denominator would just be equal to the scalar 1. So that's how we would do that for an FIR filter. Now I want to plot this, and right now I'm going to show you how to do it plotting on a linear frequency axis. And like I said, first I'm going to show you how to do it in radians per sample, but we generally don't want to do that, but I'm just being complete here. And I'm going to only show it on the positive side. So we learned how to do a single-sided signal spectrum. Now we're going to learn how to do a single-sided frequency response plot, because that makes sense. So I create a vector in radians per sample from 0 out to pi with some spacing. And there's no reason why I have to pick 0.0001, and often that's just a little too fine of a spacing anyway, but I'm going to pick that spacing so that my final result gives a nice smooth curve. And I might zoom in a little bit to see just how jagged that is. But that just is, 0.0001 almost always works. And like I said, in audio work, we're mostly interested in single-sided plots here. So now this is my go-to way of calling freq-z. So even if I'm not interested in plotting versus W, I almost always create W in radians per sample, because that's my go-to way of doing freq-z. I put in W in radians per sample, I put in my numerator and denominator, and it gives me a vector that's the same size as that and the same orientation so that my plot will work. So those are the values of the frequency response computed at those discrete time frequency points. Now I'm going to plot it. So I'm again doing two subplots. I do my usual normalization. I convert, so I do magnitude, log 10, 20 log 10 to get it in dB. I do the angle, and I do the unwrap to get it unwrapped phase in radians. If I want to see it in degrees, I would multiply this whole result here by 180 divided by pi. Okay, now I rarely, if ever, really want to plot it versus discrete time frequency in radians per sample. Just showing that for completeness here. So here, instead of recreating my F vector, I could do a similar kind of command here to recreate F and then convert to W and put it in. But look, I settled on doing this command this way. I need the W, so I make the W. Then I need to convert it into hertz so that I get the corresponding F vector. It'll be exactly the same size, and every element in F will be the correct Hertz value for the corresponding value in the W vector. So this is just converting 2 pi to Fs. That's the conversion factor, right? Just like you can convert dollars and euros with the conversion factor, we have the conversion factor between radians per sample and Hertz. Now I'm going to plot these. So now I'm plotting versus F. And so that's the most common way. So again, I make it in radians per sample only because that's my go-to way of doing freq Z. And then I convert the W into F and plot my frequency response versus that. So there are ways to call freq Z differently, but this is my go-to way, and I'm offering it to you. So you can see how to do that, and maybe that will become your go-to way. Now, we also talked about single-sided spectra for signals on a log frequency axis. We almost always really want to see our frequency responses on log frequency axis. So here it's a little trickier. So I'll show you the tricks that I use to do that. So the first thing I do is I know the range of frequencies that I am interested in. They have to go between 0 and Fs over 2, but I'm going to use the log space command so that I get nice equally spaced points on my frequency axis, on my log frequency axis. So this is different from using the FFT command where I said, oh, you might get some extra wide spacing at low frequencies and some ultra narrow spacing at high frequencies. Here, because we're not using the FFT directly, freq Z will accept frequencies that are spaced any way that we want them. So I'm going to use the log space command, and the things that I put in here tell me the powers of 10 that the frequencies will range from. So if I put a 1 in here, that's telling me go all the way down to 10 Hertz. So that's not bad. And if I put a 5 in here, it's telling me go all the way up to 10 to the 5th Hertz. And then I put in 1,000 here. I might pick a different number there if I need more closely spaced points. So I might put 10,000 or 5,000 in there if I see that my plot is a little too ragged. But I'm just using 1,000 here. Now, here is the tricky part. I cannot evaluate a discrete time filter at frequencies above Fs over 2. That's out in the replica areas. So I just created something that goes up to 100,000 Hertz. So that's going to be, unless my Fs is 200,000 samples per second, which is pretty high. Every once in a while, we might end up with a Fs up in that range, but not very common. So I've got frequency points that are above my allowable range. So this little trick just says, first here, find all the points. It just gives you kind of a pointer vector for all the points in F that do not exceed Fs over 2, and then it uses that pointer vector to extract just those elements. So if you're not familiar with the indexing methods within MATLAB, I'm not going to cover that here. That's just general MATLAB stuff, but you really need to nail those things down. So go off somewhere else and learn about those. Yeah, I have some videos on YouTube about that. That's for my EECE 212 class. So you can find some MATLAB videos there that will take you through these details. So now I've got an F that's going from 10 Hertz up to Fs over 2, or maybe just a little less than that, because there's no guarantee that that F is going to have a value right at Fs over 2. Okay, so now here's the next trick, same trick as I showed you on the previous page. I've got things in Hertz, and my go-to way of calling freq z puts in radians per sample there. So this is just converting. So I divide by fs, multiply by 2 pi, same little trick I did on the previous slide. Now I've got my frequency points in discrete time frequency, and I plug them in here, and now I get my h. But now I'm not going to plot h versus w. Nope, I'm going to plot it versus f. So now I can do that. And here, yeah, I'm saying, yes, there is some built-in way to call freq z using f in hertz, but I don't remember how to do that. My philosophy is have one way to call freq z and always call it that way unless I absolutely have to go figure out an alternate way. So now I'm going to plot it. And since I want to put this on a log frequency axis, I'm going to use semi-log x. And now I have my f vector. Now there will be no warning because my f goes only down to 10 hertz, or you can make it go lower or higher, but it doesn't go all the way down to 0. Certainly doesn't go to negative values. So MATLAB will give you no warning there. So that's okay. And we do our usual ABS with 20 log 10 and our angle with unwrap. This will plot in radians if you want to see it in degrees. I said that already. Multiply by 180 divided by pi after you do the unwrap. And so I'm only showing you how to do the plot versus continuous time frequency here because that's almost always what we want to do. Okay, so that was given the filter coefficients for the transfer function. So suppose instead you're given a vector h that holds values of the impulse response. Now, MATLAB can only have finite number of elements in that vector, so in a sense, we're kind of limited to doing only FIR filters here, but here's the trick. If we fill H with elements from an impulse response for an IIR, if that filter is stable, which is almost always the case, that impulse response is decaying down. So if you just keep going out far enough so that that impulse response decays down to values that are essentially negligible, how do you know? Well, just through experience. So you have to play around with it a little bit. But so we can effectively and approximately do this trick for IIR filters as well. So I take the vector h and I put it in here. I'm treating it as if it's an FIR, even if it is just some range of values for an IIR. It looks like the coefficients of the numerator polynomial of an FIR filter. So I put a 1 for the denominator. And then I have to put in a W. And again, my go-to method is W goes in radians per sample. So I use one of the methods that I've already talked about. If I want a log space, a log frequency axis, I use the tricks that I gave you on the previous slide. So that's how I go about finding the impulse response, or finding the frequency response, knowing what the impulse response is. Okay, filter design. That is a huge subject within DSP, and there's lots and lots of commands within MATLAB for doing filter design. So I'm not going to go into a lot of detail here for general filter design. In fact, I'm not going to talk about the main way of doing FIR filter design at all in this course. We would use the so-called Parks-McClellan method, which uses the MATLAB command FERPM, PM for Parks-McClellan. So I have some videos on YouTube from my Signals and Systems class. That's my EECE 301 class that talks in detail about how to do the Parks-McClellan and how it works and so forth. In audio, we're actually more than likely to be dealing with IIR filters. And part of that is that a lot of digital audio is striving to simulate or emulate the analog audio circuitry that was designed back in the heyday of audio. And since those were all RLC circuits, they're IIR filters. So That's what we'll mostly focus on here is IIR filters. So I'm just going to give a brief review of a few MATLAB commands for designing some IIR filters. Again, I go into a little bit more detail on this in my Signals and Systems class, and I'm sure you can find lots more detail online about how to do these IIR filter designs with MATLAB. But I'm going to focus on these 4 commands: butter, Chebby1, Chebby2, and a lip. So butter and Chebby are named after people who pioneered either actual filter design in the case of Butterworth, or pioneered the math that went into filter design in the case of Chebyshev. So if you want to design a Butterworth IIR, and later in the course we'll talk more about what it means to be a Butterworth IIR filter. But for right now, this is the easiest way to call the Butterworth command. Again, there are more ways to call this, so you can check out MATLAB help to see how to do that. But this is the most common way. You set the order of the filter, so that's going to be the number of coefficients in both numerator and denominator in this case, and you set the cutoff frequency, and it will automatically give you a low pass filter. So again, there are ways to design high pass and band stop and so forth. So you can find those other filter types just by going to MATLAB help and typing help butter. So the 0.5 is the cutoff frequency or the pass band edge, but it's in normalized discrete time frequency. Hey, remember when I took that W and divided it by pi? That's what we're talking about here. So 0.5 here corresponds to pi over 2. And so if I were to run this command, I get these 2 vectors. And then how did I get these? Well, I just did my freq command. So I made a W that went from 0 to pi, and then I normalized it when I plotted it. And so here is an example where I'm plotting it versus discrete time frequency, not because that's what I usually want to see, but I'm just checking, did my design really work? Because the design is specified in terms of discrete time frequency, at least normalized. So here is the magnitude plot in dB. Here is the phase plot in radians. And I put on a red line here to show how the phase corresponds to a linear phase response. And we'll talk more later about linear phase filters. FIR filters will give you a linear phase. IIR filters, not so much. But in audio, linear phase filters are not nearly as important as in things like radar and sonar and digital communications and scenarios like that. But there are some cases where you want linear phase in audio, in which case you're going to want to do FIR filters, but we're not going to focus on those too much. And then here's a pole 0 plot for this Butterworth filter design. And we can see something interesting. There's 7 zeros right there at the -1, 0 location. So it's -1 on the real axis. So that's this position is both minus pi, right? Minus pi and plus pi on the frequency axis. So that's what's making this go down to 0 in non-dB and minus infinity in dB. And then this is interesting. It's like the wall of poles on the imaginary axis. And that's a characteristic of discrete time Butterworth filters. Later in an upcoming video, we'll see the structure for continuous time Butterworth filters. And you might wonder, why in a digital audio course are we going to talk about continuous time filters? Well, I just told you that a lot of digital audio is focused at mimicking analog audio circuits. So we kind of want to know how those things work. And how did I get this plot? Well, that was with the Z plane, and I talked about that in the previous note set. Probably should have had a slide in here talking about Z-plane, but I don't. Here's the Chebyshev. So this is Chebby 2. Do I cover Chebby 1? Nope, I guess I just skip over the Chebby 1, but you can check that out. Here's an example of Chebby 2. Here I put in the order, and my animation's a little off. I show just the B vector, and you can see the A vector there is also 7 elements long. So I'm going to undraw your attention from those curves for the moment. So that sets the order. This is going to set the stop band height. It's really negative of that, as we'll see in just a bit. And this sets the stop band edge. So you run that, and you're going to get a B and an A vector. In this case, those will have 7 elements each, some of which may be 0, but probably not. So here's the 2 coefficients for the transfer function. And now you just do freq Z, and you can plot in magnitude in dB and phase in radians. So I've done the unwrap command here. You see that you still get some discontinuities in phase when this goes through a 0, right? So we've got a bunch of zeros on the unit circle. So as I'm going from 0 to pi, that's this progression. When I get out past pi over 2 and I get around 0.7 pi, I hit that 0. And so that's going to go to 0 in non-dB and minus infinity in dB. So at the locations of those zeros, and we'll see more about this later, I get some discontinuities in the phase. Those are discontinuities that the unwrap command does not fix. So more on that later. And again, I'm comparing to a linear phase just so that you can see what happens here. So again, I'm showing these on a linear discrete time frequency axis just so that I can see the characteristics here. I would normally, to see how those would work in audio, I would want to plot those on a log continuous time frequency axis, probably going from 10 hertz up to whatever my fs over 2 is. So that might be, for a typical fs of, we'll just bump it up to 48. That's also a common digital audio sampling rate. That would go up to 24 kilohertz. So, all right. And again, we see that Chebyshev 2 puts a bunch of zeros on the unit circle, not all at plus or minus pi, some spread out over the range. So we get these nulls. And then a wall of poles, but not on the imaginary axis. Okay, so again, this is low pass. You can check out help for filter types. Oh, I should comment, right? 0.7, here's 0.7. So that is the stop band edge. Notice that this was the pass band edge. So you have to keep these things straight. So the stop band edge is right here. And this is the stop band, I say height, but it's really the stop band attenuation because the height is really negative of that. So you can see, oh, here's minus 60. So that 60 goes to minus 60, draw a line across. Yes, it never pops up above that once we go past the stop band edge. So it works. That's why I plotted it on this linear discrete time frequency axis. But to really see how it would interact with an audio signal, I would do it on a log CT axis. So you could run this command and replot it if you want to see what it looks like. And then here's the elliptical IIR, not named after somebody with the last name Ellipse. It's named after some of the mathematics that comes into this. So now again, we have order that we set. Now we have a new thing. This sets the pass band ripple and the stop band height. Both of those, I believe, are in dB. And now we're back to pass band edge. And this default is for low pass. If you want other types, you can check out the help command. And so here it is. So here's our 0.5. And so you can see after 0.5 pi radians per second, we enter or we leave the passband. And so the 60 here sets, well, I didn't really plot this very well. I should see a minus 60, and I didn't draw very accurately there. But these heights here should not pop up above minus 60 value on the magnitude in dB. And so that all works. What we can't see is if we zoomed in here into the passband, so if we zoomed into a narrow swath here, we would be able to see the ripple. So maybe you want to do that and then zoom in and look. And again, we're looking at the phase, and I'm comparing it to a linear phase just so that you can see how it deviates from that. And again, we get zeros. We can see that it also, like the Chebyshev, puts some zeros on the unit circle, so we get these nulls that correspond to these jumps in phase. Okay, so lots of interesting stuff there. So we've designed a filter, or somehow been given a filter. So we have the B coefficients and the A coefficients, respectively numerator and denominator coefficients. And so we use those in freq-z to analyze what the filter is going to do. So we can look at it and see, oh, it's going to pass nicely frequencies in this range, and then above this cutoff, it starts to attenuate, and we see 60 dB or more attenuation up here in the stop band in this region of frequencies. That's all analysis, understanding what the filter is going to do. But if we want to apply it to some signal, so we've recorded a guitar, for example, and we have those samples in a x vector, little x vector, and we want to filter that to hear how the filter sounds, what impact it has in a sound sense to the guitar signal, we need to implement the filter or apply the filter, and that we use the filter command. So that's what we mean when we say implement. So in MATLAB, we're not implementing this in real time. That we would have to do in outside of MATLAB and write some C code or some machine language code or something like that. But in MATLAB, we can implement it in a non-real-time sense, run the vector through it, and then look at the spectrum that results or listen to it using the sound command and things like that. So the filter command, we can implement either FIR or IIR, and the structure for the filter command is somewhat similar to the structure for the freq-z command. And again, there are multiple ways to call this. I'm going to show you the one and only way that I do it every time. So if you want to see the other ways, you can type help filter, but I'm warning you, some of those are crazy and confusing, so be careful. So we have the numerator coefficients in a vector B, we have the denominator coefficients in a vector A, and then we have the signal samples in a vector X, and so that's what we're saying here. These are time domain samples. We analyze and think about the filter in the frequency domain with that path number 3 that I talked about in the previous video, where we think about Fourier transform of the signal times the frequency response. That's not what we're doing here. This is time domain samples. Okay, a little bit of a lie. Later on, we'll talk about something called overlap save and overlap add, where we will actually do the filter computations or implementations using that path number 3 view, but it'll be very complicated. That's not what we're doing here. Literally, this filter command does nothing more than recursively solve for the output samples, given the filter coefficients, and given a stream of the input samples. That's all that it does. So notice lowercase, lowercase, okay? Time after time, I see a handful of students every year thinking that they implement a filter by multiplying its spectrum times the frequency response of the filter, or that somehow we put a frequency spectrum in there. Nope, that's not what we're doing. Okay, so keep that in mind. There is an alternative to the filter command, and that's called the convolution command, or just CONV is what MATLAB uses for that. Now, technically, inside MATLAB, we can only have impulse responses that are finite duration. So technically, we can only implement an FIR filter this way. But remember a few slides back, we said, oh, well, an IIR filter that's stable, its impulse response will eventually decay. So you might just be able to take a long vector of the impulse response that eventually decays down to some small numbers, and then you could use the convolution command. Not necessarily the best way to do it. It might take a lot longer to run that way than doing the filter command, but if you don't have the filter coefficients and all you have is the impulse response, then you're pretty much stuck doing it this way. So we're going to let H hold the samples of the impulse response. And so if we think of this, even if it is intended to be an IIR, where this is a long vector that decays down to a sufficiently small value, we can still think of it as it's essentially an FIR filter. So those will be the B coefficients. So we could actually put that H in as the B in a filter command and then put in 1 for A. So we could do it that way, but I'm trying to show you this convolution command because there will be times when we'll use this convolution command. So we're going to put time domain samples in the vector X, lowercase, right? Time domain samples, everything consistent here. And then we take our H vector and our X vector and we convolve them and we get an output. That's the Y vector. Okay, so I do want to point out a subtle difference between using the filter command and using the convolution command that sometimes gets lost on students. So when we're trying to understand the structure of commands, it helps to just go to the command line and play with some simple, small examples just to see how things work. So here's a very short impulse response, not a terribly useful one. And here's a short time domain signal, again, not terribly interesting. And then I convolve them. And if you do this convolution theoretically, if you go back to my signals and systems class, you'll see that I talk about how to visually and graphically analyze this convolution. You'll see that you get these numbers out, and that if this is at n equal to 0 and this is n equal to 0, this will start at n equal to 0. And we can deduce what the length of this would be. So another way to think about that is not, kind of semi-graphically. So I remember the convolution process is you take one of these, flip it. So here I am flipping it, and shift. You just keep shifting by 1. And after you've done each flip or each shift of the flipped one, you multiply it by the corresponding values in the input, add up those products, and spit that number out. So let me just take you through that. And also, the convolution command assumes, it has to in order to do its computation, it assumes that there are zeros preceding and following whatever the signal is. And also zeros preceding and following whatever the impulse response is. I just didn't show those here. So I take it, I flip it, so now it's running backwards. I take the impulse response, flip it, and I align the n equal to 0 positions. So technically, whoops, I didn't want to do that. Technically, I should have zeros out here, but we're not going to show them. So in that first position, with just a flip and no shift, that's going to be computing the output at time equal to 0, n equal to 0. So look what I have. 0, I'm looking at the products. 0, 1, 0, 0, 0. So I only have one non-zero product. I add up all those products and I get 1. There's my output. Now the next step is I shift this forward by 1 position, and now I'm going to do products again. So I'm going to have 0 times 3, 1 times 2, 2 times 1, 3 times 0, and then a bunch of zeros after that. So now I have 2 non-zero products, and I add those up. So I'm going to have a 1 times a 2 and a 2 times a 1. Add those up, and I get 4. That's my output at n equal to 1. And so on and so on. Now I'm going to have 3 plus 4 plus 3. That adds up to 10. And so on and so on. Now, here is the thing. Notice that it takes, in this case, 1 less than the length of the impulse response before the impulse response is fully firing with all cylinders, so to speak, with the input. So these first, in this case, these first 2, because this is length 3, so 3 minus 1 is 2, the first 2 samples are not yet completely interacting signal with system. It's not saying that those are not correct. It's just saying you need to understand that. And then when we get to the end, notice that here's a position where everything is interacting with a signal sample. But then the next one, only these 2 are interacting with signal samples, and this one is not. And then the last one that I show, this is going to be this interacting with this. So that would just be a 1 times a 3, and so on. And obviously I didn't show that all the way to the end. Well, I didn't take this all the way down. So that's the idea, and there's the values that I get. But here's the thing. These first 2 values here, yeah, I think I should have, I might have screwed up my numbers here, but the point is that the first, in this case, the first 3 minus 1 values are ramp up, and the last 3 minus 1 values are ramp down. That's why things are not quite correct. This should be, I don't have the right values here, right? 1, 2, 3, 3, 3, 3, 3, 2, and 2, not 2 and 1. That's why I get a 6 here. So that's how this thing works. And we need to be aware that we're going to have some ramp up stuff and some ramp down stuff. So you need to be aware of those. It's not those are wrong values. It's just that the signal and the system are not completely interacting. It's perfectly okay, but you're going to see that in your signals. And sometimes you're not getting the full effect of a filter until your signal is kind of completely interacting with that. So I call those ramp up and ramp down. And so now let's see what we have for the filter command. If we do the same example for the filter command, we look at the output that comes and we see, oh, a 1 and a 4. That's the same ramp up that we had here. But notice that it stops at 15, right? There's 17 and then 15. It doesn't show the ramp down. That's just built into the programming of the filter command. They could have shown that, but their decision for other reasons, which it's not important why, but MATLAB's decision to stop it there is so that the filter command will, 1, give you the same number of samples out as was in, which isn't really true of what a system does. And also, the other reason it does it is that sometimes we then want to switch to maybe a different system at this point, and that would be the logical place to switch. But that's outside the scope of this course. So just comparing them. Both of them have this ramp up, but the convolution command gives you the ramp down, which really is going to be there. and the filter command doesn't show that. It stops before that. So just keep that in mind. And now I'm just showing you here what the filter command really does. It just recursively computes the difference equation. So for this, it's a simple 1, 2, 3, 1 on x, 2 on x of n minus 1, and 3 on xn minus 2. And here's our input. We're assuming zeros prior. Since this is an FIR filter, I don't need any initial conditions, so I don't really need to fill in anything there. And it just recursively computes it until we reach the position of the last value of the input. And then it stops. It could continue on, assuming that there are zeros following the input, but it chooses not to do that. That's MATLAB's choice. And here I'm just showing some of the computations and how that works. So just keep that in mind. It's a subtle difference between filter and convolution. We'll use both of those in different scenarios. And then the last thing I want to talk about is computing the impulse response. So sometimes we have a transfer function, and we could analytically find the impulse response. We could do partial fraction expansion and do the inverse Z transform and things like that. And sometimes that's useful to do, but sometimes we just have some complicated system and we have a program, a MATLAB routine that will implement that, whether it's the filter command or the convolution command or something more complicated. And we'd like to find its impulse response, not analytically, but numerically. So here's one way to do that, or two ways to do that, actually. So the first, I just used the filter command, and I used the definition of what is an impulse response. It's the response to a delta function. So I literally create a delta function. I don't need the zeros before it, because remember, the filter command assumes that anything that comes before the signal that you're putting in has zero values. So I just rely on that. So I put a 1 and then I put a bunch of zeros. And I might have to pick that n pretty large so that the resulting impulse response will decay down far enough that's negligible and I can see the behavior of this. So a little bit of knowledge about the poles of the system might help you see that, or the length of the FIR filter, if it's an FIR filter, will help you see that, or maybe just some experimentation. So I take this delta function and I put it in here as the input, and I fill in whatever the B and A vector coefficients are, and I run the filter command and I get a result, and that's the impulse response. And then I'm going to plot it. And here I'm going to plot with stem, but sometimes I might just use a regular plot. It just depends on the nature of the impulse response. If it's a short, simple one, a stem works well. If it's a more complicated one that we'll see later on with systems that mimic room reverb, then we probably don't want to do a stem plot. We might want to just do a regular plot. So it just depends. So that's one way. And then a second way to do it is using MATLAB's built-in IMPZ command. And again, there's many, many ways to call this command, so be careful. Look at the help command, or just do it this way. This is the way I always do it. The other ways are complicated and dangerous, is how I'll say it. So you put in the B and the A, and it automatically creates the H, same as up here, but it also creates the N vector that you'll do the plot against. How does it know how far to go? Well, it does automatically decide for how long to compute that. And it might not always get it right. And in fact, one of the alternate ways to call this command is to tell it some way to decide when to stop computing the impulse response values. Also note that the things that come out, even when these are row vectors, I believe the outputs come out as column vectors. So you may have some problems interacting those with other things. Notice that this is versus n in samples. And again, we might not want to do a stem plot. We might want to do a regular plot. And same here. We might not want to plot it versus samples. We might want to convert that into actual time values. So that would be take those n, take this n vector and multiply by 1 over fs to plot versus time. And I haven't said it in any of these. I should have been saying it all along. I'm showing you the plots, the plot commands, but make sure you label your axes. So let me just back up here. Notice that when I make a plot, I'm labeling my axes. Let me see if I can find, yeah, so I'm labeling what my axes are. And I'm telling you what the units are. So I'm telling you that this is in dB. I'm telling you that this is in radians. If you don't label your axes and you don't show the units, that's a useless plot. And I always say that without labels, it's not a plot. It's just art. Might be interesting art, but not a plot. So make sure that you label these. And this is probably a good time to say it. Watch the units for frequency. So make sure you understand when you're plotting in discrete time frequencies and that it's in radians per sample. Make sure you know when you're plotting in continuous time frequencies and it's in hertz. We rarely make a plot in this course in continuous frequencies in radians per second. So that would be the little omega. There may be a few cases where we do that. Okay, I think that's it. So hopefully this sets you straight on some of the MATLAB commands. And the next video will get into the real meat of the course.